Thank you very much for the warm welcome and welcome to my talk. In the next half hour, I'm going to sort of talk you through my experiences of the last 3 years building a racing simulation on the Godot engine. But before I get started, let me first quickly introduce myself. My name is Marcel Offermans. I've started programming at a fairly young age on the Commodore 64, Amiga, stuff like that. Then went to Delft to study mechanical engineering. But after finishing my study, sort of transitioned into software development because I thought that was fun as well. Also started sim racing at that time. Got a regular job in IT. Got involved in the Apache Software Foundation as well, so that introduced me to open source. And then I'd say roughly 10 years ago, I suddenly, more or less out of the blue, got the opportunity to take over the development of rFactor 2, which is a racing simulator. I jumped on that opportunity. That was already a game that was on the market, managed to more or less add a order of magnitude to the amount of users that it had over the next 6 years. And that also got me involved in a few other racing simulations. I helped out on the Automobilista game. I worked with Amazon Games on a game that you probably have never heard of, the Grand Tour game. You might have heard of the series that they broadcast. The game wasn't a big success, to be honest. And also worked on a NASCAR game together with Motorsport Games, who somewhere during that development basically made us an offer we couldn't refuse. So we ended up selling the studio. That was about 4 years ago. And at that point, I decided it's an ideal time for me to get out and start something on my own. So that's when I founded The Last Garage. And for the first few months, I kind of needed to figure out what I was going to do. And then started working on a racing simulation engine that could be used for games and other applications using Godot and a few other things. So I'll talk about that a bit more in the next couple of slides. And I want to start with just explaining a little bit more about the software architecture that's being used to build such a game. And talking about software architecture, I guess most people have some kind of understanding of what that is. I mean, it's a way of describing and making decisions about an application that you're building or system that you're building. So it's sort of like software design, but it only makes those decisions that are crucial for the success of the application, whereas the software design goes into much more detail about all the aspects of that. And a popular, at least in my days, I'm getting older, way of describing a software architecture was using the 4+1 view, which looks at a system from different aspects. So it has a physical view or deployment view. That is, where is the software deployed, on what systems. It has a logical view that deals more with your classes, your state diagrams, that kind of stuff. A process view looks at what are the concurrently running processes within your application, and a development view that goes more into how are you modularizing your application, how are you setting up all the code, building it, assembling the modules, that kind of stuff. And in the middle of all of that is the use case view, and that takes a view from the user or the different roles of your application and describes the system in that way. So going back to a racing simulation, let's start with a simple one. In this case, the use case view. There's only one really architecturally relevant use case there, and that is basically you as a driver driving a car. It's very simple. And that's the crucial one for racing. There's a lot of other stuff around that, but that's not that interesting from an architecture point of view. Let's also look a little bit at the physical view or deployment view. So where are we running this? Well, it's a game. In simple cases, you run the game on your computer. So there's just a single node, that's your PC, that's where everything's running. It gets a little bit more complicated if you actually include multiplayer, because then you probably have some kind of server, maybe matchmakers, maybe there's a place where you keep achievements and other stuff, high scores, that kind of thing. But in general, this is also quite a simple view. So going forward to the development view, it gets a bit more interesting, because if you actually look at the different modules you have in a racing simulator, there's quite a few more of them. There's obviously graphics and sound. I don't need to explain that a lot. There's a physics simulation. That's typically quite an isolated module that just deals with the physics of the car, collisions, that kind of stuff. We have a multiplayer module. That includes client and server side. Session management, that's not sessions in the sense of software or HTTP sessions, but this is more like different types of racing sessions. So you can have qualifications, you can have races, you can have maybe rally stages, you could have maybe like training stages. So that stuff is also separated from the core engine. Then there's a whole block about controllers and force feedback. A reason for separating that out in a separate module is that that's typically quite platform dependent. Most of the other stuff, I would say all of the other stuff, is not really platform dependent at all. Mostly also because that uses Godot and that's available on all platforms. But controller support is available. Force feedback is not available in Godot. Plus, I needed to couple that tightly to the physics module. So that's something I wrote myself, and that's currently only for Windows. And then on the far right, we have vehicle modules. So each vehicle is its own module, and same goes for tracks. So that tells you something about the structure of the software. And another really important view is the process view, which talks about the main processes or threads that are running. And really, that's where an important design decision is being made, because graphics and physics are completely separated from each other. Graphics, all of that runs in Godot. It's mainly a collection of all of the process functions that you all know quite well. And physics is a loop that's running, in my case, at 1,000 hertz in a separate thread. And that's just calculating little time steps of the car moving. Those two obviously interact, because the physics need to tell the graphics where is my car so we can render it correctly. Actually, because the physics is running at such a high rate, we don't need to extrapolate anything. If graphics want to render a frame, you just grab what the current physics state is and you render that. It might change if displays go over 1,000 hertz, but for now that's not the case. So, and graphics cards need to be a lot quicker for that as well. So that's how that works. But that separation is quite important. And running that physics loop strictly real time at that speed is also a little bit of a challenge. It also means that you need to read inputs at that same rate. So that's all connected. You also want to connect that to multiplayer. So your packages don't get any extra latency waiting for someone to send it over the network, stuff like that. So that's an important view. I'm skipping the last view because that gets more into classes and state diagrams, and that would easily fill up the rest of this talk. But this gives you a high-level overview of how this is all built. Now there's two big open source projects I'm using. One is Godot, I'll get to that in a minute. The other is the physics engine. I've been building racing games for a while, so I know that's very important. And you need a bespoke physics engine to do really high fidelity vehicles. At the same time, there's a lot of stuff available in open source, so I would be crazy if I built everything from all the vector and mathematics and all of that stuff myself. So I've been looking around, and a project I bumped into that has a lot of building blocks that are interesting and useful for me, that's Project Chrono. And it's really a toolbox that offers all kinds of components for not just vehicles, but building all kinds of robots. They have finite element analysis. There's terra mechanics, all kinds of stuff you can build out of that. And if you just look at their website, they have tons of videos of all kinds of mechanical systems that they're simulating. Not all of that happens in real time. You saw this little animation of a car driving through sort of deformable terrain. We can't do that in real time yet. You were just watching a video of a simulation that ran a lot slower than real time. But it's a great toolbox, and if you're building something with physics, it's definitely worth looking into. And like Godot, they have a vibrant community of people using it for all kinds of stuff. So that was also for me a great basis to get going. I was the first person, I think, to build racing cars on top of that stuff. So there was quite a few things missing, but I could easily add those myself. Then why Godot? And I was here yesterday, and a lot of people have been asking me about that as well. Why did you choose Godot? There's so many game engines around. And for me, that has a couple of reasons. First of all, having experience with the other game engines out there, I really wanted an engine that had forward rendering, or forward plus rendering even, that's a big bonus, and not deferred rendering. Racing cars move at speed, typically at high speeds. Deferred rendering engines tend to have all kinds of motion artifacts when things move quickly. So you have all kinds of little blurry effects behind cars and stuff like that. And those are things you really do not want to have for this type of game. So that was one reason. Another one is lightweight. Well, it's just me developing stuff on my computer. I know if I want to do stuff like multiplayer, I'll have to run multiple instances. So all of that is a lot easier if you choose an engine that's lightweight by itself. And obviously other things is I quickly saw it has a great community. I got involved in that really early when Godot 4 started doing alpha builds. I'm always getting great feedback and help from people if I got stuck on something. I had experience with Apache Software Foundation doing open source, and that was great as well. So I know those communities, and I know if you give something, you get a lot back from them as well. So I really wanted to have an engine that's open source. Also because it gives me the freedom later to use that code in different ways and not have anybody else saying, nah, you can't use my engine for this or that. So that was why I chose Godot, and I'm still very happy that I did. Now, what have I been doing for the last 3 years? Well, there's a lot of groundwork you need to do before you can get anything going. So I spent the first year and a half, I would say, building that foundation and building what in software terms is the first vertical slice. So the first demoable piece of software. And in January 2024, I had that ready, and I showed that to the public for the first time. So that was just one car, one track, and you could drive, and that's basically it. And the reason for showing it that early was that I wanted to get feedback from people on what the driving experience is like. That for me is core to a driving simulator. You have to be able to jump in a car, immediately get that feeling and enjoy the driving. So I went to a sim racing event for that, where people have experienced other simulators and stuff like that. I really got positive feedback on that, so that encouraged me to return the next year with a little bit more than just a vertical slice, and basically go all in and say, well, let's put 8 rigs there, let's have a multiplayer competition, let's also broadcast that live on YouTube. So I needed to add a lot more multiplayer, broadcasting tools, stuff like that. And that all went well as well. So I was then getting at a point where I had a core that I could use for different projects. And well, because you're starting to show that engine, others start to notice, and you start building contacts. And pretty soon after, I was partnering with a company called Motorsport in Motion. They actually were founded by a rally driver who does all kinds of driver training. And they wanted to build a rally simulator. And actually, they wanted to build a rally simulator where not just the driver, but also the navigator could sit in a rig, watch outside through the screens that we have, and together drive that car. So it included the full rally experience, where, not sure how familiar you guys are with rally driving, but the first thing you do when you get to a new rally is that you drive a stage at normal road speeds, and your navigator takes a book and notes down all the different turns there are. So you basically make what they call pace notes. And once you've done that, you go back to the start, and then sometime later that day or the next day, you get one try to do that all, but at speed. So it's important that you get your notes right, that you read them at the right time, and that whole interaction between driver and navigator, that's what we're simulating in that rally simulator. And that's all connected to a single computer. So it's basically running 2 rigs from one computer, each with its own function. And it was quite cool to see how people react to that, how they work together, the mistakes they make, etc. So that was a cool project. So then we went on to another commercial project with that same company, actually, for the Dutch Army, where we ended up building, and we're still working on that, a truck driver simulator. Dutch Army has about 3,500 of these trucks that you see in the image. These are big Scania trucks. They have 8 wheels, all-wheel drive, so there's a lot of power and a lot of weight. And they need to train a lot of drivers to drive those things, and drive those things in difficult conditions like fog and snow and rain and through rough terrain. But also just basic vehicle maneuvers like reversing into a parking spot, stuff like that. And right now they're doing all of that with the real trucks, which gets very expensive. And yeah, if people make mistakes, it gets even more expensive. So we're building them a simulator, and you see a little photo of that as well. It's sort of a big version of the one that I have on the showcase right here. And this has kind of an extra terminal, because you have the driver sitting behind the really big screens, 65-inch 4K screens, so that's quite big. And there's an instructor on the other side, and the instructor sort of monitors what the driver is doing. So they have all kinds of missions or lessons that they can run with that simulator. And it's still sort of mobile. You see it's on wheels. Well, it doesn't go through normal doors. It's quite wide, actually. But you can sort of move it from A to B if you really want to. So that was important to them, so they can take it to different locations for training. Another cool project I'm working on is with a Dutch sports car manufacturer, Donkervoort. You might know them. They make way too expensive cars for me, at least, but they're super cool. And with Heusingveld, which is a Dutch hardware company. They make pedals, steering wheels, shifters, that kind of stuff. And with the 3 of us, we're on a mission to sort of create a digital version of the cars that Donkervoort makes. And we're trying to, basically replicate them and also build their new cars into the simulator to do more of the vehicle testing that they do in the simulator. Because before this project, they were basically doing all the testing in real life. So they build a prototype of the car, they rent Assen or Zandvoort track to go there, and they go testing, and a lot of things go wrong. They go back to the factory, fix them, go back again, and that's how they develop the car. So that's quite an expensive process. And we're trying to see how much of that we can improve on by having a simulated version of the car as well. It's still ongoing, so the jury's still out on how well that works. But so far it's very encouraging, and it's a lot of fun to see how they build cars and what they know about them, what they don't know about their own cars, that I do need to know to put it in a simulator and stuff like that. So that's a very interesting one as well. And then finally, making the jump back to gaming, I'm working on Monosim, which is going to be the first game that will be released hopefully in Q4 this year. And Monosim is a game about the BAC mono. And like Donkervoort, I'm also working with them to model their car. And actually the picture you see, and it's a bit dark and a bit faded out, but they have a big driving simulator with a motion platform and everything, and a big 180-degree curved screen around that. And they use the simulator there also for their driver testing and driver training, stuff like that. So a bit similar to the Donkervoort setup. And together with a company called Flatout Simulations, I'm building a game around that car with all kinds of different driving experiences. So that's what I've been doing. Looking ahead a little bit, and since I'm at a Godot conference here, I'm going to take this opportunity to highlight a few things I would like to see in future versions of Godot. I know I have nothing to demand here, but I can always give suggestions, right? So I'm doing that right now. One of the things I'm running into is I would like to have some optimized rendering for a set of viewports. Viewports are now mostly or totally independent in Godot. So simple things like I want to have auto exposure. I have 3 screens. I can't get the same auto exposure on all 3 screens because it's done for each screen individually. So if one screen ends up a bit lighter than the other, you get differences. And for a driving game, that's not what you want. There's a few other things like shadows that could also be optimized in the same way if you know that these are 3 views into the same world or from the same perspective. I always want lower latency in graphics. In audio, I think there's still some improvements to be made there as well. I also ran into the problem that I would like to have support for multiple sound cards at the same time. That's a bit of a niche use case because I use the normal sound card for generating sounds, obviously. And the second sound card is often used for generating vibrations. So we have typically bass shakers attached to a rig, and that gives you feedback on vibrations that you feel from the car. And those are really just bass speakers that you hook up to an amplifier and you generate sounds for them. But I can only access one sound card from Godot. So I had to make my own sound engine to do the other one. I think that's something that might be improved, and I don't know if there's other use cases for it, but that's it from my point of view. And a final one is large world support, and that mainly revolves around accuracy when you're further away from the origin. If I want to make a racetrack or a road that's like 20 kilometers long, if I go away from the origin too far, my accuracy with single precision floats is too low to keep driving. My physics engine has solved that. That's all double precision. There are double precision builds for Godot, but I think there's also some other solutions that might be interesting to integrate into the engine as well. So those are things I'd love to engage with the rest of you guys to see if we can make any improvements there. Final slide, just in time. If you want to help, want to know more, I'm at the showcase. You can always contact me afterwards as well. And if you have any questions right now, I think we have a few minutes left for questions.
All right, thank you. Yeah, I'll go there.
Thank you.
You talked about specifically choosing Godot because it has a forward plus rendering path. And one of the reasons you don't want to use deferred is because they deferred rendering tends to have artifacts with fast-moving objects. I'm not the best expert in rendering pipelines, but I'm not sure that you probably only have those artifacts when you use TAA, or is it that deferred rendering has that artifacts like by default, or how?
No, a lot of it is TAA, and a lot of it is also a typical setup. I mean, I've seen a few other companies building racing simulators on, for example, Unreal Engine. Let's use that as an example. And I just see, I mean, they know what they're doing. I'm not a graphics expert either, right? So there might be solutions, but I just see them struggling to get the performance right with the deferred rendering and get rid of all those artifacts. And it might be just TAA, it might be more. I'm not entirely sure. But coming from a forward rendering engine, which we built ourselves, we didn't have any of those problems. We have other problems with forward rendering engine, like having many different lights at the same time. That's a challenge. That's a bit better in Godot, but it's still a bit of a challenge. So that's really why I was choosing, let's go with forward rendering. It eliminates all the problems. I have enough problems left to solve, so that's why I'm choosing that. I'm not saying it's impossible with a deferred rendering engine, no.
Okay, thank you.
Right, I see two
wow.
questions there.
There's even one at the back.
All right.
Have to run for your money.
Yeah.
I'm curious about your large scenes that you talked about.
Yeah.
Could you dive a little bit more into like the specifics of what you came across that is like not working for you?
So the naive implementation is just create a large scene, and if you're too far away from the origin, you get accuracy problems. There are ways to solve that. I could compile Godot with double precision, right? That would solve a lot of that. I am actually not sure how many people here, for example, are using Godot with double precision.
None.
That makes me slightly scary about how well tested that is. I'm not sure. Maybe that's just me. Maybe it's fine. But I didn't want to start using a build that almost nobody uses. So that was for me a solution that's a little bit out there. Other solutions would be, and one I'm actually using right now, is if you don't want to be 20 kilometers from the origin, instead of moving the car out 20 kilometers, I can just move the track to the origin instead of the car. That works. And then I wanted to use Terrain 3D, because that's also a cool plugin, and it doesn't support that.
Yeah.
So then I ran into other problems. So I'm not saying it's not possible to do it or that it's not solved, but I think it's an area where we can, as a community in general, improve a little bit more and offer developers more solutions to that.
Yeah, exactly. It's an interesting topic.
Yeah.
Were all physics running on the CPU or GPU as well?
No, physics are all running on the CPU, on a single core, in fact. Yeah.
Okay, thank you.
Yeah.
Are there any plans for hardware acceleration, for example, on like graphics cards?
I have one friend who is also into building physics engines for vehicles, and he actually has been trying for more than half a year to build a version of his physics engine that runs on the GPU. And so far he has not succeeded in doing that. So I keep in touch with him in case that works, but I haven't seen examples of that yet that work. Would be a great solution because it gives you a lot more power, but yeah.
Okay, thank you.
Yep. Are you actually going up to the last row in the corner? Awesome.
Yes, I am.
You showed a variety of different simulators there. And obviously in a high performance application, the driver feels the car moving through their backside, so they like to have a motion simulator. Sorry, it's really awkward to hear your own voice and talk. Have any of the simulators you worked on been motion simulators? And with the static simulators, have you accounted for the fact that they are static simulators and they lack that lateral movement?
That's a great question. Yes, I've worked with two simulators that support motion. One has more or less 6 degrees of freedom. That's the one at BAC. You saw a little bit in the image earlier. So that one's supported, and it tries to convey the G-forces as well as it can, right, given the limitations we have on Earth. I also have one where you have sort of limited motion. So it has a few degrees of freedom, and it uses some of the vibration for feedback. It also has seatbelt tensioners. So when you brake hard, it pulls on your seatbelt, so you get the same sensation of braking hard. And those are all cues you try to give to replace the real G-forces that you would feel in a car. There's always a lot of discussion about motion simulators because all of them are mechanical by nature, and they always introduce some form of latency because they need to move actuators, and that actually takes time. If that latency is too big, the motion doesn't help the driver anymore. It's nice as an attraction, but it doesn't really give you the right cues. So in general, motion should only be added if it's done right, and that can get very expensive. If you don't have the motion cues, then yeah, you have to resort to other tricks to help the driver get the same feedback that he would get in a real car. So you end up doing things like maybe add some volume to the tire noises so you can hear better when the tire's at the limit of grip. You wouldn't hear that in a real car as much because there's much other noise that drowns that. But that helps you get some kind of feedback. Obviously, we have force feedback on the steering wheel. That helps. Some form of force feedback is even possible on pedals these days, which is really cool. That helps with feeling things like traction control, ABS, because that gives kind of vibrations back through those pedals. So yeah, you're resorting to tricks, and I'm implementing some of those, adding more over time. But yeah, we'll never get perfect there. That's unfortunately the conclusion. But we try to substitute with things that actually help the driver. Thank you.
Very insightful. Thank you.
All right, perfect. Thank you for the questions. Thank you for the presentation, Marcel.
You're welcome.
We'll make a quick change again, and then we'll have the next presentation.
Excellent. Thank you.